we have introduced pointers which are used to hold the address of memory location. In order to directly work with memory location, apart from storing the addresses, we also need some mechanism to obtain the address of memory location. The address of operator is meant for that, which is our next topic of discussion. Whenever we define a variable, whether built-in type or user-defined type, memory gets allocated for it. The address of or the ampersand operator can be used to obtain the address of the allocated memory chunks. The address of operator, when applied over a variable or an array element, gives the address of the first byte of their storage location. It is important to note that the returned address is the address of the first byte. The address of the first byte is also called the base address. Let us walk through a code sample to understand this better. In this code sample, the first line defines and initializes an integer type variable. This statement will get 4 contiguous bytes allocated for the variable named var. We can also use var like a tag attached to the memory location through which we can access and modify the content of the memory location. The left hand side of the second statement declares an integer type pointer variable named ptr, which will allocate 4 bytes for it. The right hand side is the place where all the magic happens. On the right hand side, the ampersand operator is applied over var, which returns the address of the first byte of the 4 contiguous bytes, which were allocated to var during the execution of the first line. This statement prints the value held by ptr. As per example, ptr is holding the address of the first byte allocated to var, which is 114. You will see the hexadecimal representation of 114 getting printed. It should be noted that 114 is just a hypothetical value chosen for illustration. The actual addresses are long integer values. It should be noted that the format specifier for printing pointer type variable is %p, similar in the case with arrays. This example illustrates the usage of ampersand operator for element of an array. The first line creates and initializes an array of 3 integer elements. The second line creates an integer type pointer variable and initializes it with the address of the first byte of the third element of the array. Array will be discussed in detail in the next lesson. For the time being, you just need to understand the style of application of address of operator, which is the same whether it is an ordinary variable or an array element. A discussion on address of operator will not be complete without discussing the restrictions applicable to this operator. We should clearly understand and note down the condition under which this operator either may not give expected results or may not even compile. Ampersand operator is not applicable to expressions of any kind. During the evaluation of expression, the intermediate results as well as the final result reside in registers of the computing unit and not in the primary memory unless you assign them to regular variables. For this reason, memory addresses of expressions are not defined and hence application of ampersand operators over them will get stuck in the compilation stage itself. For example, this statement will not compile. If you look at the expression on the right hand side of the assignment operator, you can see that we had tried to apply the ampersand operator on an expression. On the other hand, if we assign the result of an expression to a variable, the addresses of such a variable will certainly be defined and can be obtained by applying the ampersand operator. For example, these statements are valid and will work fine. Observe that the result of the expression sin x plus 20 has been stored in a variable named var and address of var has been fetched by applying ampersand operator over var instead of applying it over the expression itself. Memory addresses of numeric literals are also not defined because of the same reasons mentioned before. For example, this statement will not compile because the ampersand operator has been applied over float type literal, whereas this statement will compile smoothly because the literal 3.8 has been assigned to a variable named var and the ampersand operator has been applied over var instead of the literal directly. For the same reason again, the ampersand operator is not applicable to variables declared to be stored in registers by making use of the register keyword. In this example, the first line declares count to be stored in registers by prefixing the keyword register in its declaration statement, whereas non-register type variables have perfectly valid addresses and the address of operators can be applied over them without causing error. See the example on your screen. In general, it can be stated that as far as a user-defined C program is concerned, the memory location available in registers do not have addresses associated with them. And for this reason, application of ampersand over entities residing in registers is not defined. We have seen the applications and limitations of ampersand operator. Since pointers are also variables, they also occupy memory for getting stored. Let us try to understand the amount of memory consumed by a pointer type variable. Size of pointer type variable. Whenever we define a variable, the compiler allocates a certain amount of memory for it. The amount of memory allocated depend upon the type of data which the variable is expected to hold. For example, defining an integer type of variable gets 4 contiguous bytes allocated for it, and defining a long integer type of variable gets 8 contiguous bytes allocated for it. Pointer type of variable is no exception. It is also expected to hold a value. Only difference in this case is that the value held by a pointer type variable is the address of a byte of your primary memory. It is important to understand that pointer variables hold the address of a single byte of memory. It is immaterial which is byte. That byte could be the first byte of the contiguous chunk of 4 bytes allocated for an integer data type, or could be the first type of a contiguous chunk of 2 bytes allocated for a short data type, or could be any random byte from your primary memory. Just like regular variables, pointer variables also need memory for storing addresses. Whenever a pointer type of variable is defined, the C runtime allocates a certain amount of memory for it. The amount of memory allocated depends upon the architecture of the operating system. In a 32-bit system, 4 bytes are allocated, whereas in a 64-bit system, 8 bytes are allocated. Hence, the size of the pointer type variable will always be either 4 or 8 depending upon the underlying platform. We can verify this by making use of the size of operator, which is a very handy operator to get the number of bytes allocated to a variable of any type. The first 2 lines of this code snippet declare 2 pointer type variables of char and integer type respectively. The third and fourth line prints the amount of memory allocated to them by making use of the size of operator. On my 64-bit system, the output of the third and fourth statement were 8 and 8 respectively, which is the size of a char and an int type of pointer variables respectively. This illustrates that the size of a pointer type of variable is independent of the data type with which the pointer variable was declared. We have finished stating and explaining pointer definition, and we have also seen the application of address of operator to obtain the base address of variable. The next section talks about dereferencing operations.